Good evening. Good evening. I'm Massimo Roberto, and I have the pleasure and the honor of moderating, guiding us through this fascinating encounter with two protagonists, two absolute superstars of contemporary astrophysical research. I was thinking, preparing this meeting to myself, 50 years ago, I was at the age when you climb trees. You climb trees because they are there. You climb the tree because you can reach farther out. And you climb higher and higher, and you reach the last branches, paying attention. You reach the last, and then on that evening, on those evenings, we discover that beyond the last branch, there is the moon. The moon is within reach. They were landing on the moon. And for people of my age, and the age of Jonathan, I will say, that was a life-changing experience. We realized how powerful is the attractive of reality, the provocation of reality, something that calls us to go beyond, to go farther, to stay curious, to climb the highest mountain because it's there. And because at the end you learn something from you. All the great climbers and explorers will tell you, I did it for myself. Because perhaps we want to know how far we can go trying to affirm something there that calls us. And today, this is clearly expressed in a most powerful way through scientific research. Science is done exactly for this reason. Reality is there, attracts us. And we want to know. We want to explore. We would like to even go there. And at the forefront of scientific research in these days, probably the hottest field of contemporary astrophysics is the discovery of planets around other stars. We are discovering a treasure trove of worlds. And we wonder, now the question, if we are alone in the universe, if there are other places where we can live, is more and more real than has ever been in the past. It was a philosophical question. Well, now it starts to be a scientific question. So to know where we are and to see the implication for our awareness of ourselves, we have invited here Jonathan and Karin. I must say their biography is so long that I can just basically invite you to take the program and go through because it will take forever to read it. But just let me say a few words to frame who we have here at the table this evening. Jonathan is David Duncan Professor in Physical Science and the director of the Center for Astrophysics and Planetary Science at Cornell. So he's the boss of Cornell University, one of the historic centers in astrophysics in the United States. He's interested on how planets form, evolve, what processes maintain and establish habitability, the possibility of finding life, and what kind of environments may host the chemistry sophisticated enough that can support life. Jonathan is a protagonist in the exploration of the solar system. He worked on the radar and other instrument on the Cassini probe that went to Saturn. He's a co-investigator in the Juno mission, and we are talking about Jupiter and the Europa mission going to be launched in the next few years that will probe one of the most fascinating bodies of the solar system, Europa. Is also, I must say, interdisciplinary scientist for the James Webb Space Telescope, so in some sense is my boss. I answer to these guys. He is a member, of course, of several academies, starting with the National Academy of Science. He is chair of several NASA, National Science Foundation boards, strategic planning committees from NASA, etc. Read the biography. I think this is enough. Karin, it's even more scary because Karin was a baby genius, unlike me. She was champion of Sweden of chemistry. She went to the Olympics in chemistry, and immediately at the end of high school, she went to Caltech, which is, as you know, number one university in the field. So Sweden, Caltech, and after Caltech, there is no other place in the world except Harvard. So she went to Harvard. She had a little detour for 1 year. University of Virginia tried to get her 1 year. Harvard immediately captured her, and she's now professor at Harvard, professor of astrophysics at Harvard. Karin is interested in a fascinating discipline, which is astrochemistry, which is basically the chemical processes they appear around in the universe. And of these chemical processes, the most fascinating, as she will tell us, those that are germane to the formation of life, early molecules, complex molecules, amino acids, whatever she does. She will let us know. She works a lot also in the lab, so we have really the full complement of exploration and sort of experimental theoretical activities here this evening. I think I told too much. It's time to listen from them. Thank you. Jonathan.
Okay. Thank you, Massimo. One of the most profound questions that we can ask as human beings is, in what way are we special? Are we alone in the cosmos? From the spiritual point of view, we understand how we're special. From the scientific point of view, the question really is whether there might be other kinds of life elsewhere in the cosmos, intelligent life. And the first step in understanding that is to know how many planets there are elsewhere in the cosmos. And this is a question that has fascinated people for centuries. If you go back 800 years, you find that St. Albert the Great in the 1200s asked the question, is there one world? Do there exist many worlds or but a single world? This is one of the most noble and exalted questions in the study of nature. Now, he decided on the side of one world, but he also had a lot of great insights about the universe. He thought the Milky Way galaxy, for example, was made of stars, long before the telescope was invented. And then we go on even into the 1300s, Dante and the Divine Comedy. If you read the very last line of the Divine Comedy, it talks about the love that moves the sun and the other stars. And so already there was a realization within the European framework that the sun was one of many stars. But it wasn't until Copernicus and his publication of his book and his model that the Earth, in fact, was not the center of the cosmos, but instead that it revolved around the sun, as did the other planets, that people began thinking about the question of how many other planets might there be. And in the late 1500s, Giordano Bruno, who was not a scientist, but rather was a philosopher, if you will, thought about this and wrote about it, in Italian, of course. And what he said was that there must be countless worlds. If there are countless suns in the heavens, then there must be countless planets, all rotating around their suns in exactly the same way as the 7 planets of our solar system. But then he went on to say something very important and very profound, given the fact that he wasn't a scientist and the telescope was just being invented. He asked the question, why don't we see these other planets? Why are they invisible? And he answered his own question by saying that we see the suns, the stars, because they're self-luminous, they're very bright, but we don't see the planets because they're simply too dim. They're lost in the glare of their parent stars. And that statement was exactly correct. And in fact, if you look below the statue of Giordano Bruno, there's a modern image of a star as seen through a telescope on the Earth. The light of the star has actually been blocked out by a disk called a coronagraph. And even though that light has been blocked out, some light escapes. It escapes around the edge of the disk. It's distorted by the Earth's atmosphere, by the optics of the telescope. And so if you want to see a planet at the position of the Earth around that star, you have to look most of the way into the center where the glare is. It would be impossible to see the Earth. The planet that you do see, which is indicated by the arrow, is very far from that star. It's the equivalent of being out at the edge or beyond the edge of our solar system. So this was recognized back in the late 1500s and early 1600s. But interestingly enough, as modern astronomy progressed, the question of whether there might be other planets began to be less interesting in the 19th and 20th century, partly because it turned out to be very difficult to solve the problem of how do you actually find these planets, how do you pull them out from under the glare of their parent stars. So here's an old textbook which is one that actually I used as a freshman taking astronomy in 1976. It's entitled Introductory Astronomy and Astrophysics. And there are 3 chapters in this book on the solar system. And there is not a single mention anywhere else in this comprehensive treatment of astronomy about planets around other stars. There's nothing at all. So the field became kind of quiet for a long time, and it eventually began to blossom again because astronomers found ways to, using tricks essentially, to find planets around other stars. And after more than a decade of efforts with these techniques, which I'm going to tell you about in this talk, planets began to be found. And so now the field of what's called exoplanets, planets around other stars, is one of the most popular and exciting branches of astronomy. There are textbooks written and popular books written. This is a textbook called Exoplanets, edited by Sarah Seeger, who's a prominent exoplanet astronomer at MIT. And if you go to websites like exoplanet.eu, you'll find every day the number of planets is increasing, almost every day. The number of discovered planets when I pulled this off the web was 3,975 in 2,970 planetary systems. So some of those systems have multiple planets, 653 of them. And what astronomers have found is that for every star, on average, for every star in the Milky Way galaxy, there is a planet. Now, we haven't looked at every star in the Milky Way galaxy for a planet. This is extrapolating from discoveries made closer to our own solar system, but the statistics are pretty good. On average, there is one planet for every star in the Milky Way galaxy, which means there are perhaps 200 billion planets in our galaxy. Now, how do we actually detect these planets? How have these things been detected? And I want to spend a good part of my time on this question because I think it's important to show how astronomers use physics to tease out the signature of a planet from underneath the glare of the star. So in this lovely animation that was prepared by the Planetary Habitability Lab at the University of Puerto Rico in Arecibo, you see 5 different ways to detect planets. And in 2 of those cases, all but one of those cases, you're actually not looking directly at the planet. You're looking either at the effect of the planet on its parent star, or you're looking indirectly at the effect of the planet on the signature of another star behind it, which I'll describe in a minute. That's microlensing. So let's start out. Yes, this is an astronomy lesson, and yes, there will be a quiz afterwards. So let's start out with that panel on the upper left, that animation. And what that animation shows is a planet and a star. Now notice that the planet is not actually orbiting around a fixed star, which is the way we think of things when we think of our solar system. Both the planet and the star are orbiting around their common center of mass. So if these 2 objects were equal in mass, if they were 2 equal mass stars, they would actually be orbiting around a center that's exactly halfway between them. But because the planet is much less massive than the star, the planet makes a big orbit and the star makes a little orbit around that center of mass, which is shown by the red cross in the diagram. Now imagine also that that planet is invisible. You're the observer on the Earth. You really cannot see that planet. It is lost in the glare of the parent star. So how can you find the effect of that planet? Well, one way, which was the way that astronomers in the 60s thought would be the only way to do it, is shown in the box below. It's called astrometry. And essentially, if you imagine now taking that animation of that star wobbling around the center of mass of the system, imagine it's a point, the way that stars look in the sky, and you're looking at that in the night sky. You would see that point of light making a small circle relative to the fixed background of stars. And that's all that astrometry is. It's observing the cyclical or periodic motion of a star caused by a companion. Very simple technique, and the little box is attempting to depict that. By the way, those numbers underneath each box are the number of planets discovered by each technique, but several years ago. This slide is by now a bit old. So, in fact, each of those techniques has discovered between 2 and 3 times more planets. Okay, so that's astrometry. It turns out it's been very difficult to make astrometry work for various reasons. So another approach, the one that really broke the field open, is shown on the upper row in the middle, and it's called radial velocity. Now, you see the star in that little panel there becoming red and blue, and then red and then blue again. So what's happening? To understand what's happening, you have to imagine taking that image of the star and turning the whole thing 90 degrees so that it's facing you. Or even better, I'm going to be the star. Actually, I am the star because I have the stage right now. So I'm going to be the star, and I'm going to make my little orbits, okay? And you are the observer. So here I go. I'm making my circle, okay? Now, for part of the circle, I'm moving side to side from your point of view. But in other times, I'm moving toward you, and I'm moving away from you. Okay, now, when I'm moving toward you, the light that I'm emitting, because I am, as a star, a self-luminous object, not that way in real life, but some people try to get students to claim that, but no one's willing to sign up to that. As I'm moving toward you, the light that I emit, the wavelength of that light, the color of that light, the wavelength gets shortened by the motion, my motion as a star, okay? So if the wavelength gets shorter, I'm going to appear to be bluer. When I'm moving away and emitting light toward you, the wavelength is being stretched out, and so now I look red. So just by this motion, radial motion, back and forth as part of the small circle, I'm turning blue and then red and then blue and then red. Now, the problem is this. The change in color is so subtle that you really can't see that. And so what astronomers have had to do is to use a technique that's time-honored called spectroscopy, where you spread out the light from the star using a prism, or actually today we use something called a grating, and you can see the individual wavelengths of light. And in that spectrum from the star, there are dark lines, cutouts, where atoms in the atmosphere of that star, at well-determined wavelengths, determined in the laboratory, are absorbing the light. And so those are fiducial lines in the spectrum of the star. Now, as the star moves toward you, those lines are going to shift toward the blue, shorter wavelengths. As the star is moving away, they're going to shift to the red, longer wavelengths. And that's what astronomers learned how to observe very, very precisely in the 1980s and 1990s, and that broke open the field of planetary, of exoplanets. And radial velocity was the first technique to really detect a lot of planets. Okay, another technique, transit, which is in the upper right, a little simpler. So now I'm going to be the star again, and this little clicker is going to be the planet. And it happens that the orbit of the planet, the plane of that orbit, is nicely aligned to you. That most of the time doesn't happen, but occasionally it does. So as the planet is sweeping around in front of me, it's partly blocking my light. Okay, here I am, a luminous object, and this unilluminated planet is blocking part of the light. So as you can see in that depiction, the light of the star dims as the planet passes in front of it. And it does so in a very regular periodic way, once each orbit of the planet. Now, in order to detect these transits, you have to be able to measure the brightness of the star very, very well. It's a drop of about 2% for a planet the size of Jupiter. It's a drop of, 1% for a planet the size of Jupiter, about 1/100% for a planet that is the size of the Earth. So the best way to do this is to go into space, and NASA's Kepler mission became really the king of planet discoveries using the transit technique, discovering more than 3,000 planetary candidates. Okay, last 2 techniques. One is called microlensing, very exotic, depends upon general relativity. How many people have taken general relativity in the audience? Okay, so very quickly, what Einstein realized was that, can we do a whole course on this? No. All right, so what Einstein realized was that massive objects bend light, distort the path of light through space. And so a star is a massive object. So imagine a situation where you have a background star in the distance, and because stars in our galaxy have some random motion, foreground stars will occasionally pass in front of the background. You can't see that with your eye, but it can be measured by telescopes. So when that foreground star passes in front of the background star, the light from the background star gets bent by the gravity of the foreground star, bent in such a way that it's very much like a convex lens. And the starlight, the background star, will temporarily brighten, as you see in that panel on the bottom center. But if you look at that panel, you'll notice that after the slow brightening and dimming, there's a sudden pulse. And that sudden pulse happens if the foreground star, the lens star, has a planet orbiting around it in just about the right position to remagnify the image of the background star. You can think of that planet as a kind of a distortion on the lens that represents the foreground star. And so if the planet's in the right place, there'll be a second sudden brightening, and boom, you have a planet. That's a tough technique to use. It requires staring into space at a large number of stars. Not very many planets have been detected that way, but it's an interesting technique. And then finally, direct imaging, which is the technique of trying to block the light of the parent star so that you can bring out the faint light of a planet. There's a lot of work being done to make that technique sensitive enough by going into space to be able to actually see another Earth out from under the light of the parent star. So these are some of the tools that are used on the ground, observatories, and in space. You see Kepler at the bottom right, and a new telescope, the Transiting Exoplanet Survey Satellite, just launched last year, picking up from Kepler. I want to focus, there are thousands of planets that we know of. I want to focus on one really interesting system called the Trappist One System. The name of that planetary system, the first one to be discovered by this particular group in Europe, does pay homage to the Trappist order of monks, not their religious devotion, but the beer that they apparently produce and that these astronomers drink. And so indeed, that's the case. That's why they named it. So the Trappist One System is one of the most interesting systems because it has 7 planets orbiting around the star. And those 7 planets are in really tight orbits around that star. In fact, the farthest one is closer to its star by a lot than Mercury is to the sun. So it's a very compact system. And furthermore, the star itself is a small star. If you look in the lower right on the slide, you'll see a little piece of the sun. And scaled to the same scale is the size of that star, the Trappist One star, which is quite a bit smaller than the sun. In fact, it's really not much bigger than the planet Jupiter. And then the planets of that system are about the size of the Earth down to about the size of Mars. So they're considerably larger than the moons of Jupiter, which one might have thought would be a fair comparison. So there are these planets, these 7 planets from Earth to Mars size orbiting around this star, and we'd like to know, are any of them habitable? Could they support life? What we really want to know is, are they too close to their parent star where the water would boil off? Are they too far away where the water would freeze, like on Mars, or is it just right? So it turns out that you can do a calculation, and you can lay out these 7 planets on a graph according to the amount of light that they get from this small red star that is their parent star. And indeed, it turns out if we take the Earth and we say that the amount of light that the Earth gets is equal to 1, that one of those planets gets the same amount of light from its parent star that the Earth gets from our sun. And that might be the habitable planet in the Trappist system. So how do these planets form? If there's so many planets in the galaxy, what is the process by which these planets are created. And the answer seems to be a very old one that goes back to Laplace and Descartes, which is that planetary systems form in disks, spun out as the gas and dust that will become the central star collapses from a much larger, maybe something a light year across, down to something the size of our system, our solar system. And it turns out that all of this material, this nascent material in the galaxy from which stars form, has a little bit of rotation to it. So as it collapses, just like an ice skater, when she pulls in her arms, when she's spinning, spins faster. As this material gets more compact, it spins faster, eventually spinning so fast that the centrifugal force pushes material out into the form of a disk. Now, in the 50s and 60s, astronomers didn't believe this because they couldn't figure out how to get the mass from the disk, the matter from the disk, into the star and leave the rotational momentum out in the disk itself. But astronomical observations showed that disks are very, very common. And this is a beautiful, very recent image of a disk of the HL Tau system from ALMA, a radio telescope system in the Atacama Desert in South America. And you not only see a disk, but you can see cleared lanes in that disk, probably the result of planet formation happening. Early planets having just formed and cleared a lane of dust and gas out from the disk. So astronomers, as far as they can tell, find that many stars, perhaps most stars, as they're forming, spin out disks, and that's why planets are so common. But how do you get from the dust to the planets themselves? Well, we're learning about that in our own solar system. New Horizons spacecraft, which visited Pluto a few years ago, just passed the most distant object ever investigated directly by humanity. It's an object called Ultima Thule, well beyond the orbits of the giant planets, out about 40 times or more the distance of the Earth from the Sun. And it's a kind of a museum piece that shows us that smaller bodies stick together and grow to bigger bodies. So here this is two pieces that have stuck together to something about 20 miles across. And if the process had continued, there would be growth to bigger and bigger things. We can simulate that growth in a computer. And so what I'm going to show you very quickly is a simulation done by myself and two colleagues, where we start out material in a small, sort of around the size of the moon, and we use the gravity of Jupiter to stir that material up to make larger bodies. So we start out with this material. The red is closer to the sun. The blue is farther from the sun. The red material, because it's close to the sun, doesn't have much water in it, and the blue has a lot of water. And as time goes on, as you can see, the planets closer to the sun are going to grow to be bigger, but notice they're going to change color because they're getting material scattered by the gravity of Jupiter, which contains a lot of water, and that's going to be added to their mass as they grow. So it's quite possible that in our own solar system, the presence of Jupiter was important in delivering water, which we need for life, and organic molecules, which we also need for life, from the outer part of this disk, which was cold, to the inner part where the Earth was forming. So hundreds of billions of stars in our Milky Way galaxy, hundreds of billions of planets in our Milky Way galaxy. In the cosmos at large, there are hundreds of billions of galaxies. I'm not going to try to multiply those numbers together. You can do it yourself. But it's a lot of planets. And the question then arises, could there be life on those planets? You'll hear more about that from Professor Öberg in a minute. But I want to close by emphasizing something, which is that all of these techniques that I've told you about depend upon our confidence that the laws that we can determine in the laboratory on the Earth and nearby us in the solar system are operating across vast cosmic distances. And that assumption that the laws of nature are immutable and reliable and constant comes not from science itself. It comes from the Western tradition. It comes from the Judeo-Christian tradition of understanding that our universe is a creation of an omnipotent God who has made for us a place that is regular and predictable, and which we can therefore study. And this comes from both biblical and traditional sources. For example, I quote here from the letter of St. Clement to the Corinthians, where he says, "The sun and the moon with the company of the stars roll on in harmony according to his command. The unsearchable places of the abysses, the indescribable arrangements of the lower world are restrained by the same laws." And so long before Galileo trained his telescope on the heavens, it was realized that this universe, this created universe, with its regularity, was there for us to study as a kind of a grace, as a kind of a gift. And in doing so, we're learning marvelous things about our place in it. Thank you.
So it's a true pleasure to be here, so thank you so much for coming. So I will just move on directly from where Jonathan and Professor Lunine ended and talk about how we try to figure out the probability of that there is life on other planets and its connection, as it turns out, to how we think that life originated here on Earth. So we live in an era where we know that stars are not just cold stars, they're worlds with their own planetary systems. And that's going to be where we spend most of our time thinking about life on these systems. But before going there, I want to spend a couple of minutes just thinking about the importance of astronomy in general, of understanding our cosmos in general, for having a relationship with God and understanding God as a creator. So if we go back to the religions that were in the Middle East before God revealed himself to Israel, and when they looked up on the skies, what they would see is something like this. The skies were alive with gods and demigods vying for their favors, providing blessings and curses. What the Hebrews did to this cosmos was incredibly dramatic. They killed off the gods. They killed off the gods for a creation that was spoken into existence, that was peaceful, that was good, where instead of a son of the god and a son of the moon, you had two lamps. Instead of heroes being spread out in the sky, in the form of stars and constellations, you had little lights. Now, the Hebrews' understanding of their God certainly informed their cosmology, but there was also things about the cosmology that must have informed their understanding of God. If we look at what it looks like, so the physics of this cosmology, it's a vault, it's a flat Earth, it's an underworld. This is a contained cosmos where it's quite easy to imagine where God is. He's outside of this cosmos. Now, this cosmology was replaced by the time that we have the early Christian church with the cosmology coming out of the Greek word, which incorporated both new data and new physics. The new data is that the Earth is round. It's been known for a long time. The new physics is the Aristotelian physics, which takes telos very seriously, that things are moving towards where they're meant to be. Now, this cosmology, too, must have informed their early Christians' view of who God is as a creator. This is cosmos that's incredibly well-ordered, where things are moving in the right directions, so an icon of the ordering within the creator himself. Now, this cosmology, too, was replaced for the church under quite dramatic forms as the heliocentric cosmos came into being in the 16th and 17th century. Now, in itself, moving the center of the cosmos from the Earth to the Sun might not seem like a very big change, but when combined with the physics, the mechanistic physics that developed at the same time, we get a very different cosmology, a clockwork cosmology. And God becomes a mathematician that creates this perfect cosmos, winds it up, and then it goes on forever. This is a cosmos that doesn't really need a God to sustain it in the same obvious way as the vault or the pillars under the earth would need a God to sustain it. Now, this cosmology continued to develop into the 19th century, mainly becoming bigger, and also for metaphysical reasons becoming eternal. Now, there's nothing really that could have... we don't want to put limits on God. He could have created an eternal universe if he wanted. But there are some difficulties in intuiting how to put the creation in Genesis, how to fit that together with an eternal and infinite cosmos. If you live in a cosmos that has always been there, you don't really have to ask the question of when was it created or who created it. So maybe it's not so strange that by the turn of the 19th to 20th century, you find that a lot of physicists are atheists. Not all. We have some very famous Catholic scientists from the time, but many are. And at least this disconnect between the cosmology of physics and the cosmology of the faith must be some of the reason. But then something happened, starting in the 19th century and developing in the 20th century. And what happened when we look in astronomy is that through a combination of Einstein's equations and the genius of Father Lemaitre, we realized that we don't live in a universe that's static. We live in a universe that is developing over time, that's emerging from something very small and very simple into something very big and very complex. We see it in cosmology. We see it when we look at individual stars and planets. These two, we now know, have a beginning. They have an end. Every year, 7 new stars form in our galaxy, and a few stars go out of existence. And we also see it in biology. I mean, this is supposed to be something that's controversial for Christians, but in fact, I think it's part of this beautiful cosmology that we now inhabit, where we constantly see new, interesting diversity that is emerging from something much simpler. This, too, should change how we view God as a creator. We still have God the mathematician. I mean, we still believe, as Jonathan alluded to, that this is a world that's governed by physical laws on all scales. But if we look at this emerging world, we also see God the artist, who is still in the middle of creating his masterpiece. And of course, we know through Revelation that he then does the incredible sort of scandalous thing of stepping into his creation to save it, but more about that later. So this is God the artist this seems to be God who just enjoys seeing things developing and giving this sort of ridiculous dignity to his creation of getting to be co-creators of their own destiny. Now, what I would claim with Professor Lunine is that with the coming of exoplanets, we have once again changed the cosmology that we live in. And the question is, what does that tell us then about the Creator? Well, I think it mostly just reinforces what we already was learning during the 19th and 20th century, that this is a God that really enjoys a variety of created things. But this, of course, leaves the question of, if we have all these planets around other stars that are words in their own right, how many of them are living words? So what will we one day encounter extraterrestrial life? And I think most interestingly, from a theological point of view, will we encounter extraterrestrial intelligent life? And how should that affect our theology and our understanding of God and our relationship with him? Now, to start answering, what is the probability that there is life out there, it's a natural place to start with the one planet we know of that has life, which is Earth. Now, on Earth, we can trace back the origins of life by looking at the pattern, the genetic pattern in living and extinct life forms. When we do that, we find that we can trace all life on Earth back to a lost common ancestor that lived somewhere around 3 to 3.5 billion years ago. This is probably not the first life that emerged on Earth, but it is an early life form. And up here to the right, you see Darwin's first attempt at this sort of tree of life. Now, the question is, how did this first life happen? We don't know for sure. We think that the scenario like this is reasonable, and that something like this must have happened. Where if you go back to the very early Earth, so right after the Earth had formed, we had a moon impact, things had cooled down a little bit, so that's sort of 4 billion years ago. We had water, we had chemicals that through the laws, building on the laws of physics and chemistry, combined into more and more complex molecules in this prebiotic scheme. These more complex molecules then combined into forming RNA, which is very similar to DNA, but somewhat simpler in structure. This RNA word eventually became complex enough that you had all the functionalities of living creatures in it. That developed further into the DNA and protein-based word that we have today, and around 3.5 billion years ago, you have this last common ancestor of all current life. So the question is then, this very first step of having the right kind of chemicals around, how common is that on other planets? Obviously, we should also continue to work on getting this part here right. But at least, let's see if we can have as a sort of a lower limit on how much life there can be in the universe of how often that you end up with the right kind of chemistry on these planets. And what the right kind of chemistry is debated. There are a couple of different scenarios. The scenario that I find to be the most plausible is the one pictured here, where through a combination of a water-rich word and hydrogen cyanide, turns out to be much better for origins of life than for sustaining it, is abundant. And through this hydrogen cyanide-based chemistry, you can actually form all the building blocks of life as we know it today. So another way to ask this question is, how often do exoplanets have water on them and have the right kind of chemistry? As Jonathan was alluding to, what I was talking about, one of the most exciting systems that we have found is this Trappist system. So this is an artist's impression of what it would be like to stand there on that planet D, that perfectly temperate planet around this very small star. Now, as you can see, there's lots of water here because it's the right temperature to sustain liquid water. But just because you're at the right temperature doesn't mean that you actually have water around. So that's the first question we can ask is, how often do planets form from material that's rich in water? Now, planets form in disks, actually, before I get into that, the first thing to do is to look in the solar system. Now, if you look in the solar system, the Earth is not one of the most water-rich bodies in the solar system. Some of the moons in the outer solar system have far more water for their size than water does. So at least where the Earth was forming, in the disk where the Earth was assembled, water must have been very common. And if we look more generally in these disks where planets are currently forming, we can check how much water is there currently where planet formation is happening. And the answer is that there's a lot. So what's shown here is two different ways that we use to look for water in these disks. One is to look for water vapor. So that's what you see to your left. So all the little spikes there that are not in red, green, or yellow are due to water vapor in one of these disks. And then to your right, you see another spectra. So this just shows how you block or emit light at specific wavelengths or colors due to having particular chemicals or species in these disks. And what you see, these sort of broad features in the spectra, they're due to icy material in these disks. And what we see is that there's also a lot of water ice. So both in solid form and in gas form, we have a lot of water available where planets are forming. So we don't think that lack of water will be a problem for having life originating on other planets. So how about the other part? So we don't just need water. We also need hydrogen cyanide and the other chemicals that are in this diagram. Now, we would just ask the same question. If we look with telescopes at these disks, we look very carefully, do we see these kind of molecules in these disks? To do that, and Jonathan already mentioned this, we have this amazing new telescope in Chile, the Atacama Large Millimeter and Submillimeter Array. What is so amazing about this telescope is that it was built to allow us to observe two things in these disks very carefully. One is the dust, which tells us the overall structure, and the other one is what molecules are in these disks. Now, you already saw one example of a disk taken with ALMA. These are another 20 or so of them. Sometimes I just want to pause and realize how amazing it is that we can now see planets forming in action. These lanes that are being carved out here are most likely of baby planets that are carving out material as they're orbiting these young stars. Now, we can do more than just look at these disks or the structures. I said we can also look for light that's coming from specific molecules. And the kind of molecule that we were interested in, remember, was hydrogen cyanide. And when we do look for it, we do indeed find it. I mean, this is a cartoon, but we do see these hydrogen cyanide molecules in these disks. And it's there often. It's there in large abundances. So if we put this together, what we have is that we have lots of planets around young stars. Many of these planets seem to be of the right temperature to be habitable. They have the right temperature to sustain liquid water, to have the kind of life that we have here on Earth. Now, beyond that, we have also seen that water is abundant where planets are forming, and it's therefore very likely that they are water-rich if they are at the right temperature. We've also seen that we often have the right organics, which means that they also are likely to have the right building blocks for an origins of life when these planets are forming. But what we don't know yet is if any of these planets are inhabited. That is something that hopefully we will find out over the next 20 to 30 years. But I don't think it's too early to start thinking about sort of what some of the consequences could be for how we view God, our relationship with God. And that's what I want to spend the last few minutes on. But before getting to it, I think it's important to realize that there are two kinds of extraterrestrial life that we could find, right? One is, let's say, bacterial or animal or vegetable life. That is one category. On Earth, it took a few 100 million years for that kind of life to first develop. Now, a few 100 million years is a long time, but it is much, much shorter than the 4 billion years that it took for rational life to develop here on Earth. It seems, therefore, that it's not obvious that just because you develop life on a planet, you're going to develop the biologically machinery that you need for rational life. Of course, we also believe that in addition to the biological machinery, you need God to especially create a rational soul for us, which, whether he always does that when he has an advanced enough creature or not, I think is a perfectly fair question to ponder. But we have this scheme that we might see life, we might see even intelligent life. Now, what does that tell us about our place in the universe? That there are potentially living words, that we live in a universe that's potentially full of living words. Well, I think one thing is that it might seem that it makes us less important than we were 20 years ago. At least that's an argument that you sometimes hear, that who are we to believe that we are especially loved and created by God if we are this tiny creature on this tiny planet, in the backwaters of a boring galaxy somewhere in the cosmos? Well, first of all, I would say that Nazareth was also in the backwater, so we should not be sad about being in the backwaters of our galaxy. But more than that, I think to claim that this is a new question is simply false. You it's true that we today know that the universe is much, much bigger than people did 3,000 years ago. But the universe has always been a big place. I mean, I like to go back to Psalm 8, where the psalmist, I think, very rightly ponders. When I see your heavens, the work of your fingers, the moon and stars that you set in place, what is man that you are mindful of him, and the son of man that you care for him? You don't need to know that the universe is billions of light years to wonder why God would care about us when we seem so small compared to the cosmos. Now, it might be that the discovery of exoplanet has made us seem less special than we were before. And we believe that all God creates in some way, in some unique way, shows his glory, an aspect of his glory that otherwise would not be there. So there are aspects of his glory that are in these exoplanetary systems that's not in ours. But I would say, on the other hand, exoplanets, the existence of planets around other stars, have in some ways made the universe a cozier place. I mean, when we're looking up at the skies, we no longer just see cold stars, we see worlds surrounding their suns. So I'm not actually sure whether we have made our place sort of more difficult to explain in the universe by adding these planets. But what if they are inhabited? Well, they might be. I would actually hope that they are. I think it would be wonderful if we were living in a universe teeming with life of all different kinds and varieties. But we're still at a time and place where we don't know if that is true. It might also be that we are the arc of the universe carrying all the life that there is through space and time. And until we have discovered that there is alien life there, this is still a possibility, which I think makes this word all the more precious. But this is all, I don't think there's anyone that's really nervous about finding life on other places as long as it's bacteria. I think where the sort of interesting theological discussions comes is if we consider the possibility of extraterrestrial intelligent life. Now, I think there are two questions that come up there. One is how it affects sort of our relationship with God. We are described as the crown of the creation in Genesis. That argument I don't find very troubling or convincing, I guess. We already know there's at least one other intelligent species in the universe, and that has not in any way had a damaging effect on us. And on the contrary, the angels have been very helpful to us. So we already know that the universe is full of these alien species. That should be a comfort. But the other part has to do with incarnation, which I think is where the potential trouble enters. Now, if there are other species out there, they may or may not have fallen. Considering that the only two intelligent species we know, well, I guess every kind of angel is their own species, but the only two kind of beings that we know have fallen, maybe just a third of the angels, but there seems like there's still a high number. So it seems like it's not totally improbable that if you have another intelligent life, that they would also have fallen, and therefore they need to be saved. Now, could they have their own incarnation? Some people believe yes. Some theologians believe yes. I would side, and I really encourage you to read this book by Marie George, which does a Thomistic analysis of aliens. It's fantastic. I would side with her and say no. It seems like God can, of course, do what he wants, but it seems both from Scripture and from theology that this was a one in a universe kind of event for God to step down into his own creation and die. But then if we have the incarnation and other species don't, that seems incredibly unfair, right? I mean, they don't get this sort of direct biological relationship with their Redeemer. They might not hear about him for 1,000,000 years. Does that seem right? Well, to that I would say that we too had to be grafted onto Israel. So it does not seem completely improbable that God would work out the salvation for other species by grafting them onto humanity. And 1,000,000 years is a long time, but the people in my native Sweden had to wait 1,000 years. Before they found out about Christ. So this seems like part of how God works, that he really likes working through a small group of people and saving the universe through them. And finally, I just want to say that I think I would be extremely excited about the encounter with aliens. I think when we have encountered these other intelligent species, angels, they have revealed things about God to us that we did not know before. I'm certain that if there are other rational species, then God has revealed himself to them in some way. And getting to hear their stories about God, I think would give us a whole new set of information and understanding of who God is as a creator. So with that positive, I guess, ending, I am happy. I'm going to hand it back to Massimo.
I don't know what to add. I'm amazed and grateful because this event gives us the possibility of meeting people like Professor Lunine and Öberg, and give us the possibility of continuing this conversation among us and with them, just outside. It's time to close this meeting, but I think our hearts are full of wonder and questions, and really, we are around out there. Let's continue if you want, and keep moving with these great questions in our heart. Thank you. Have a good evening.